Sir, am I audible to you?
Yes, Deepji.
Okay. Sir, we will wait another 2 minutes and then we'll start, sir.
Okay, fine, Dr. Deep. Yeah.
Vikas sir, shall we start?
Yes, we can start.
Okay, sir. So, good afternoon, everybody. Today we are here for the third day, which we are celebrating as International Workshop on Technological Advancement in Renewable Energy, Current Scenario, Future Perspective, and Challenges. Organized by Department of Environmental Science, Amity School of Life Science, Amity University, Madhya Pradesh, Gwalior. So today in day 3, we are having fortunate to have as a chairman Professor Dr. Bikash Srivastav, coordinate professor and head coordinator, Amity Institute of Biotechnology, Amity University, Madhya Pradesh. Co-chairman Dr. Nidhi Shukla, assistant professor, Department of Environmental Science, Amity School of Life Science, Amity University, Madhya Pradesh. Invited lecture, we are having Professor S. Balachandran, Associate Professor, Department of Environmental Science, Vishwabharati University, Shantiniketan, West Bengal. Dr. Dhirendra Chaudhary, Head, Center for Renewable Energy, BVS, Purvanchal University, Jaunpur, UP. Abhishek Kumar Mishra, Dr. Abhishek Kumar Mishra, Associate Professor, Department of Physics, UPES, Dehradun. So before we are going to have our technical session today, so first I would like to introduce, and I'm very honored to introduce Professor Dr. Vikas Srivastav, who is the chairman of this technical session. Professor Dr. Vikas Srivastav is currently working as a professor and coordinator in Amity Institute of Biotechnology, Amity University, Madhya Pradesh, Gwalior. He has obtained master degree in applied biochemistry from Cancer Hospital and Research Institute, Jivaji University, and PhD in biochemistry from Cancer Hospital and Research Institute, Jivaji University. He has 22 years of teaching and research experience. He has published more than 55 research papers in various journals of international and national repute. He has filed 8 patents out of 4 are published and 1 granted. He is also member of various international national scientific bodies. He is running a two project funded by MPCST Bhopal in the area of biotechnology. Several PhD and MPhil students are working under his guidance. He has presented paper in various national and international conference and reputed podium. He has also written 2 laboratory manual for biotechnology student. He has also organized various international national scientific events. Presently, he is involved in the designing and synthesis of multifunctional nanomaterial by chemical and biological route and its application in clinical and non-clinical studies. And it is just a glance, I would say. And I welcome you, sir, on this technical session. And along with sir, his co-chairman is Dr. Nidhi Shukla, who is a assistant professor of Department of Environmental Science. His background is applied science and MSc Environmental Science, PhD in Environmental Science. His research interest is application of spectroscopic techniques on various biosamples, and his research interest on biodiversity, environmental chemistry, ecology, and pollution. I am welcome also you, madam. And before going to technical session, I'd say I'd like to request Chairman sir, please say 2 to 4 lines or 5 lines about this workshop.
So, thank you very much, Dr. Deep, for a nice introduction. First of all, I would like to congratulate to the organizing team of this national workshop. And the theme of this workshop is very relevant in current scenario. That is technological advances in renewable energy, current scenario, future prospects and challenges. So, as you know that since ancient time, the human kinds are always dependent on the various kind of renewable as well as non-renewable energy sources. Because without energy, nothing can be possible. But as we all know that there are several issues with the non-renewable energy sources, which we are using since ancient time. And the major concern with related to this is nowadays is a pollution also, and which is ultimately affecting the whole environment and creating a problem for humankind. So definitely we have to be more focused towards the renewable energy. Since last 3 decades, we can say that the people are much more focused about the renewable energy sources. And when we talk about the renewable energy sources, then definitely the sunlight, water, these are the major sources which we are utilizing. If I remember 30 years back, there was a product in the new product came into the market, and that was basically a solar cooker. Nowadays, people are not using that much, but at that time, it was a basically the fashion came into the market, and the people were started purchasing the solar cooker, and there was a definitely the advancement was not that much, so the cooking time was little bit higher, but the people got aware somewhere around 30 years back. So definitely now we are in a 21st century, and the people are looking for the various kind of energy sources, and these renewable energy sources are playing very important role for the to making India a developed country. Even the Prime Minister is much more focused about the nowadays the solar energy. That's why they have launched a various kind of programs to increase the culture of using the different kind of solar panel. Yesterday, I was reading about nowadays the solar, even the solar panels are getting replaced by the solar sheet. So there will not be a requirement of the lot of expenditure to place the solar panel at the rooftop. Now you can identify any of the place, and that sheet can be used. So definitely the awareness has increased, but still there are a lot of work which is needed in this particular area. And although these are the sustainable sources, but definitely some of the sources which is related to the like coal, like these biomass, still these biomass are having a limitations of sustainability. So that has to be taken care also. Definitely, the cost is the one of the area to use such kind of technologies in the society, and there is a need. We can say that the cost may be considered as a challenge that has to be reduced. As far as solar panel are concerned, definitely the revolution has come in this particular area uh, after a research on the in the area of nanotechnology. And nanotechnology has provided a great strength in this particular area, but still there is a need of some quality work in this area. Uh, so this should be focused more. So this is from my side, and along with us there are various good researchers like Professor. I think that I can see him. Sir, I welcome you,
Thank you, sir.
and
Thank you.
hope that this session will be beneficial for all, and
Yes.
will guide in everyone will get an insight in the area of renewable energy. Thank you, sir.
Thank you, sir. So we have our first technical session of Dr. Srinivasan Balachandran, sir. Okay. So before sir start his scientific explorations before us, first I would like to introduce sir. Dr. Srinivasan Balachandran, currently holding position of Associate Professor, Department of Environmental Studies, Institute of Science, Vishwabharati, Santiniketan, West Bengal. He is having more than 24 years experience in the field of environmental science. After passing MSc, MPhil, PhD from JNU, he joined Vishwabharati University in 2004. He is having more than 100 publications in top-rated journals in the field of environmental science. His current research interest on bioenergy production from bio-based resources, along with many national projects funded by various national funding agencies like UGC, DST, TBT. Currently, he is operating international projects like UK Research and Innovation and established bioenergy laboratory in Vishwabharati University. He also guided more than 10 PhD research scholars During his tenure, his broad area of interest are biogas and renewable energy, soil pollution, chemical speciation, and bioavailability of potentially toxic elements, polycyclic aromatic hydrocarbon, and their degradation. So I welcome you, sir, again, and
Thank you.
I would like to hear. We would like to hear from you more and more.
Yeah.
Thank you, sir.
Yeah. Yeah. Thank you, Deep, for Dr. Deep, for your brief introduction. Shall I share my screen now?
Yeah, yes, sir. Yes.
Um, is the screen visible?
Yes, sir.
Oh, 1 minute. I don't know how to enlarge it. And the
Sir,
panel,
actually, you
the
go to the. Yeah, yeah, yes, sir. Yes, sir. That's it.
yeah. Okay. Yeah. Right. Fine. Um, Good afternoon, everyone. The International Workshop on Technological Advancement in Renewable Energy is going excellently, and I'm very happy to be a part of it and proud to be a part of it. And today, what I'll discuss is about the renewable energy resources in India. And then when we talk of renewable energy resources, India, when we look, a majority of the people live in rural area. And in rural India, the energy crisis is one of the crucial issues when we talk of the rural India. There's the energy crisis, and still, and India is basically an agricultural based country with lots of cattle, agricultural residues, and things like that. Now, when we see the energy resources, people in rural India still use uh, wood, coal, and leaves as their primary fuel. Although government of India has given some subsidies for LPG and other things, but the cost and other things which the rural people cannot manage it. So I decided to give a small talk on the social acceptance and barriers for biogas adoption in rural India. So let's go into the topic. Now, when we see these days, climate change is one of the biggest burning issues, and the major cause of it is the release of huge amount of CO2. And there is a huge energy crisis in domestic sector. As professor said that the solar is one of the very good options, and in that solar option can be used for electrification and other things. But what about the cooking fuels? But so one option is the biogas, but now people, when we use, see, people use basically the dirty fuel, basically the which we call it as the solid biomass fuel, that is wood, coal, cow dung, agricultural residues, leaves, they use it. Now we have got lots of problems associated with utilizing this dirty fuel, basically the indoor air pollution, basically. Now, when we look into the indoor air pollution, which we call it as the household air pollution, HAPS. So the HAPS are basically carbon monoxide, formaldehyde, particulate matters, basically PM 2.5. And the PM 2.5, because it's more problematic when compared to PM 10, that is the particulate matter less than 10, because the particulate matter 2.5 has a very smaller surface area, and has got a, sorry, it is smaller in size, and then it has got a huge surface area, and because of the surface area it can absorb various pollutants which are present there, and it will cause serious health impacts on the human beings. as well as you will also find by burning this thing, you will find compounds like polyaromatic hydrocarbons like BAP, chrysene. All these compounds would be emanating in the indoor cooking and associated health issues. And the most affected are the women folklores, because they are the one who is cooking in this in the indoor environment. And the solution uh, is uh, we can use biogas as the one of the very good options. And when we look in India, the overall cattle population could be roughly 193 millions of cattle are there, and an adult cow can give say roughly 15 to 20 kgs of cow dung per day, and per kg of cow dung, when we look, it will give roughly 40 liters of biogas. So for a family of four, we need roughly 800 to 1000 liters, that is roughly 1 cubic meter of biogas we needed. So per day, if we can have like 15 to 20 kgs of cow dung, I think that will be enough for us, for a normal households, for their 3 meals a day, they can cook it. Now, what are the problems associated with this? When we look into the problems associated with this, the main problem is the women's, for collection of the fuel wood, they have to go for distance. So they have to spend at least 3 to 4 hours fetching the fuel wood. Not only the women, the children are also involved in this thing. And then the significant amount of rural energy is basically from the biomass. So nearby the forested area, whatever it is there, people go there to collect it, and then the forest is also deteriorating, and ultimately the biodiversity gets reduced in and around the forest. And then another important thing is, when they use the firewood, the chulas or the cooking stove which they use is like inefficient. Thereby, it increases the drudgery of women and the children as well. And then, as I said, the smoke generated in the indoor is one of the biggest problem for their health issues. So in India, we have got roughly four different types of plants which we have it. So biogas plants, which is still used in rural India. One is the fixed dome plant, where the dome is fixed, where you can see here, it is everything is underground, and this is the fixed dome, where you will find the waste coming inside, means waste is cow dung or any other waste you can put inside, and then the excess amount of waste will just the slurry which comes out. And then whatever the gas which is being produced here through the process of anaerobic digestion, the gas is being collected in the space above this, and then this is being connected to the pipe, and it can be utilized. While the second one is the floating drum biogas, where you will find here like a bottom pit, you will find it, where you have to add the cow dung slurry inside, and the exhaust pipe would be there, where you can collect the bio slurry, you can get it. And here instead of the fixed dome, you will find here a floating dome. That is, whenever the gas is being produced, the dome rises, and then it can just go up. And then in the top of it, you will find a vent where the biogas can be connected to the kitchen. And here, the third one, you will find a low-cost polythene tube digester. So here, what you do is you put the slurry inside, and the slurry slurry inlet is this side, and slurry outlet is this side. And here you will find the biogas being connected, biogas which is being collected, and it can be connected to a gas stove. And here, this is the balloon type, which is now like cost effective as well, the balloon gas. While when we say problem, we can discuss it later. So this is the balloon type. where the whenever the gas is being produced, the balloon rises, and from here the outlet is there where you can collect the biogas, which can be collected to the kitchen. Now, when we look into the biogas, what are the problems like? Just a minute. Yeah. So when we see why we use more biogas now, what is the advantages of it? Now, basically in rural India, you will find wastage is plenty. Let it be agricultural residue, let it be cow dung or organic waste, whatever it is there. All these can be degraded, and ultimately in an anoxic condition, if you keep the organic matter, it will produce biogas, which is a simple, which we call it as, it's a type of fermentation, you can say it. Without oxygen, if you keep it, it produces biogas, and one of the major component in the biogas is methane, and this methane is used as an fuel basically to cook and things. Thereby, when we use these organic waste and the biodegradable waste, like we can get a lot of energy from it. Otherwise, like when we say cow dung, now when we say cow dung, what people generally think about cow dung is it can be used as a fertilizer. Now, when we put it as a fertilizer, what we are doing is we are losing the energy which we are supposed to get from it. And when we store it, there also you will find anaerobic decomposition would be there, because when we pile upon and pile and pile and pile and we put the cow dung, from there, and the anoxic condition would be there, and ultimately you will find methane, ammonia, all these noxious gas emits and goes into the atmosphere. So we are not getting any energy out of it. So when we use it in the biogas plant, what we can get, one, we get good energy, and in the form of a biogas, the cow dung. The other thing is what we get is the biogas slurry, which we get it. This slurry can be used as a fertilizer. So you can get two things from the same time: energy as well as a fertilizer. Okay. Now, as I said, the bovine, when we look into the cow, the amount of bovine which is present in India is plenty. It has got a highest amount. That is, when I say like cows, uh, mm, uh, pigs, goat, all the bovine population, when we look at it, is roughly like more than 3 million we have got it. More than 3 lakh we have got it. So this much amount of bovine population, if we have got it, I think we no need to worry about anything else for the rural cooking energies. So, so ultimately, when we look the how much amount of cattle dung it can produce it, so it will produce roughly 980 million tons of cattle dung. If we utilize it properly, it can get roughly 70.2 gigajoules of energy annually. So the rural area, almost have got 95% of livestock, and we can get roughly 48,000 to 20 million cubic meters of biogas annually. So when we look into the agricultural household, 58% of the rural agricultural households, 22% exclusively depend on livestock for their livelihood. Let it be, if when we go to Rajasthan, you could see the goats are plenty, and if when we come towards UP, Bihar, all those areas, you will find cow is the primary thing, and 22% of India live especially on the livestock for their livelihoods. Now, Government of India also has given lots of initiatives for biogas thing. So this was started in way back in 1981, and till now, till in 2017, also we have got a national biogas commission. That is the one. Yes, that is okay. Sorry. Okay. So in 1981, when we see when the biogas plant was initiated, lot many like there was a plenty of biogas which was being initiated, like lots, and in all the rural households you will find plenty of biogas plant installed. Later, when we look, the biogas slowly decreased, and now if you enter into a village, only hardly before they used to be 20, 30 households used to have it. But now when we look, we did a survey in Bengal, like in and around Shantiniketan. They used to, in every village, there used to be a defunct biogas plant, like 10 or 15 defunct plants are there. So like whatever the government is doing now, the government has done, it's not reaching the people. So like when we look here, the which was started, the NP BD, which was started in 1981, in the sixth 5-year plan it was started. It went took off well, and then the next till 1990, almost 1.5 new million plants were established. Now after that, what a government did is in 2006 the biogas power program, off grid program was done. So thereby 25 cubic meter to 85 cubic meter plants were installed, and this is being basically done in small dairy farms and in rural industries which was being installed. And then in 2007 also the biogas national project on biogas development started till 2014, while in 2017 government once again in the 12th plan, what they did is they gave lot of money for developing the large biogas plants. That is the bio-based power generation and thermal application program was being done. And in 2017 also the national biogas mission was started. Like basically this was given to the rural, same it's like the same the old wine in a new bottle which they have given it. So when we look into the status of alternative energy resources, you will find here uh, uh, the solar uh, is almost when we look into the megawatts, you will find here. So here also you could see the wind is the highest energy producer, followed by solar, then the biopower and small hydropower. Right. And then when we look into the status of the biogas plants in India, under the National Biogas and Manure Management Program, almost 5 million family-sized biogas plants were installed up to 2017. But the major problem associated with the biogas plant is the utilization, and the government provides a lot of subsidies it has given, like from sorry, from it should be 7,500 to 12,000 it gives for 1 cubic meter and 2 to 6 cubic meter biogas plants. And then when we see here, as I discussed, the biogas plants are defunct after 1 or 2 years. Now what are the major reasons for the defunct of the biogas plants? So when we see here, what are the major reasons for it is number one, you could say the household expenditure, the family size of land holding, because when we look into the land holding plays a very important role in the deciding the biogas plant. And the caste, livestock, gender participation, social stigma, outreach, maintenance, what type of feedstocks they use it, the skill and knowledge, and negative perception, market barriers, technical barriers, environmental constraints, institutional barriers. So So there are various barriers associated with this. Now, when we look into the household expenditure, when we say more than 50% of the rural population in India, the expenditure is less than 10,000 rupees. The whatever the income is less than 10,000. And then there is a positive correlation between energy generation and energy there is a positive correlation between the income and energy, as the income enhances, the utilization of the clean energy enhances. And then the low income group has got financial difficulties in acquiring a biogas plant. So, in Odisha, there are some studies which says that the wealthier people opt for improved cook stoves and biogas plants, who are economically weaker sections. They have got it. While for installing a 1 cubic meter biogas plant, roughly the cost is 25,000 to 35,000. We get it. And the government gives a subsidy of 12,000 rupees a maximum. And then the people cannot afford to pay rest of the amount to construct the biogas plants. So this is one of the income expenditure, because they say that I cannot pay that much of amount, say 17,000 or 20,000 rupees I cannot pay for construction of the biogas plant. And then the larger family members, they are not interested in biogas plant, because they say that we have got plenty of human resources, that is, the family members are more, so they have got ample of time to go collect the fuel wood and things like that, and they use it. Right. And Yes, so whenever we see here the not only the family size is one of the very important factor to determine the adoption of biogas plant. But in olden days, I'd say not in olden days, say in 1981 and things like that, when biogas plant was being constructed, at that time people were all a joint family. Though the family was good, it was a joint family. And due to the joint family, what people did is that in their so they would one person would take care of the cow, mixing the cow dung, and other family member would pour it into it, and then the biogas plant was maintained. But nowadays it has become into a nuclear family, so small number of families, and then so they don't have time to maintain the cow dung, the biogas plant. So this is one of the barriers for adoption in these days. In say for like 30 40 years back, that was not the condition. But now the condition is like that, every household is a nuclear family. So these are the problems, one of the important observations which we observed at in and around the Bengal regions. Right. And next important factor is the backwardness of the caste. So for acceptance of biogas, religion is not a significant, but social stigma, that is the caste, is one of the important factor. Because when we look into the income wise, information wise, and other things, the SC and ST people are and other backward classes, they are not that much economically viable to adopt the biogas. And they also don't, because they are all daily laborers, and they don't have the stipulated amount of cows as well to for their livelihood, and they don't have the biogas plants. And when compared to the mainstream caste, that is the upper caste and the tribal, the upper caste have got a higher hand in terms of economy, education, economy, and other things. So adopting the biogas is easier for them. Then livestock. So when I say livestock, as I earlier mentioned, that we need a minimum of 25 kg of uh, of cow dung is required. So we need a minimum 2 to 3 cattle. So if you don't have a minimum of 2 cattle, then you cannot have a biogas plants. And the social stigma is one. Now the foul odor and the unhygienic surrounding or near the house caused by the biogas slurry is like people don't accept it, that it's having a drain type of thing, so people don't accept it, and people don't accept it that fecal matter, and cooking from the fecal matter is also a stigma, that how can I use the gas which is coming from the fecal matter and things like that, and still people use fuel wood only it. And then the outreach activities. So we need more outreach activities, that is we should use more technology, prints and medias to the rural households, thereby the cultural learning should be given to the rural people and make them adopt the biogas and things like that. And then here one more important thing is the maintenance. The Unless and until you maintain the biogas plant, the it won't survive for a long time. So this needs proper repairing and maintenance has to be there. But when we go into the rural area, there are not that much technological people who can do repairing the biogas plant. So in an panchayat, you can say there will be one person maximum to do this job, and then and that person cannot cater the whole panchayat. So, so this is one of the major problems. So we need more and more people who technical resource person must be there who can uh, 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 who can visit the village, and then there should be a proper stock register must be there, whether biogas plants is being running properly, what are the problems which are there, is there any maintenance issue is there. So these type of things has to be done. So there must be a nodal agency, and then nodal agency up to the not only in the state, it must be up to the village or the block level, it must be there. And another thing is the feedstock, because whenever we talk of biogas plant, we must see what is the feedstock which we are using for biogas plant. Now, when we look into the feedstock, generally in rural area, people use cow dung only. Now, there are various feedstocks which can be utilized as a for biogas generations, like sewage, municipal solid waste, crop residues, rice husk, bagasse, whatever material which is having a carbohydrates, proteins, lipids, the organic matter, the organic residue, whatever it is there, these organic residues can be used to generate biogas. Right. So, because if you put these organic residues outside, they will rot and giving a foul smell. And so rather than making it rot outside, you can put that into the biogas plant, and then you can get the energy. Now, say when we see here, the methane content basically depends on some of the important features. When we see here that cattle manure can give 65% methane, poultry manure 60%, pig manure 67. So like even up to the kitchen waste can give 50% of methane. Algae can give up to 63% methane. Water hyacinth can give rise to 52. So when we see here, you will see the manure means cattle, poultry, pig, farmyard manure, and the straw like rice straw, wheat straw, grasses, leaves. Not only that, even the weed, whatever which is present in the agricultural feed, that weeds also can be given. The kitchen waste, algae, water hyacinth, weeds, everything you can do it. Because one of the most common thing what we find in this is the organic content in it. More the organic content, you will find high amount of biogas we can produce it. Now, when I talk of organic content, and we must also see in which type of organic content it is present. Say, for example, the cattle, the farmyard or cattle, the sorry, the straw. Now, when we look into the straw or any plant-based materials, you will find the biogas basically is being produced from cellulose or hemicellulose. What they do is they degrade and ultimately produce biogas. So when we see the general pathway for the biogas generation is as the plant biomass, basically it must contain plenty of lignocellulosic material. Now, when I say the lignocellulosic material, it consists of lignin as well as hemicellulose and cellulose. Right. So when we fermented the first, because biogas production needs basically four important steps occurs. First step is the hydrolysis, acetogenesis, and methanogenesis. Now, when we look into the hydrolysis, whatever the organic matter is present, they are ultimately converted into glucose, basically, or a simple sugar. I won't say glucose. It is converted into simple sugars. Now, these simple sugars are converted into organic acids, basically, by acetogenesis. The organic acids could be like acetic acid, propanoic acid, or butyric acid. It could be any organic acid. It can be. Now, these organic acids are converted into acetate, basically acetate or propionate or butyrate, and they ultimately gets converted into methane. Right. So when we look, all these processes are being done in an anaerobic condition in by utilizing the various microorganisms. Right. So when I say the lignocellulosic material for enhanced for more biogas, what we need is we have to break down these lignocellulosic materials. So when I say the lignocellulosic material, what the lignin does it is the one which is very difficult to degrade, and it tightly binds the cellulose and hemicellulose together, and it is a woven thing. So in order to assess the cellulose and the hemicellulose, what you have to do is you have to break the lignin component. The lignin has to be degraded. Then only the bacteria would assess the cellulose and the hemicellulose, thereby giving rise to what you call the biogas productions. So, so when I talk of the plant waste, which is rich in lignocellulosic, we must go for this pre-treatment, which we call it as the pre-treatment. Now, when we look into the pre-treatment, there are four major pre-treatments, three major, I'll say. One is the physical treatment, second is the chemical pre-treatment, third is the physico-chemical treatment, that is the combination of physical and chemical pre-treatment, and biological pre-treatment. Now, when we go for the physical treatment, the physical treatment is a must for biogas production. Now, why I'm saying must means because in order to degrade, you have to break the particles. You have to cut it into smaller pieces. Thereby, the surface area can be enhanced and the bacteria can degrade. So how you can do it? You can do it by mechanical way, like a mechanical or an extruder or a simple chopper machine. If you go to the rural villages, we will see for the cow straw, before giving it to the cow, what they do is they chop it into small pieces rather than giving the full cow straw. They chop it and put it. So instead of making such a no, not such a huge things, you can chop it into a small pieces, and you can break the size of the particles, right? Uh, so one of the major drawback in is that you need more energy in it. So when we look into there are various techniques are there. Now when we see here, you can use like a miller is there, like a miller, a chopper, and extruders, like various grinding machines are there. So thereby you can grind it and then put it. So grinding is one of the very simpler way for the biomass to be degraded at a very fast. Now, when we go for grinding and other things, the only disadvantage is that the energy. Now you need to put energy to degrade this, to energy to chop these things. Another thing, another treatment is the chemical treatment. Now in physical treatment, what you can do also, you can go for boiling, you can heat it. So when you heat it, that is also one very good technique, you can say it. Another treatment is basically the acid treatment, alkali treatment, organosolve, ionic, and ozonolysis can be done. So these techniques are basically, you can say it as an industrial process. When we go for a huge biogas plant, like an 100 cubic meter or 1,000 cubic meter, this type of pre-treatment has to be done. This I'm not talking for regarding the small biogas plant which rural people use it. So biogas plants, when we use acids and other things, what we generally do is we break down these particles. That is, the lignin can be broken down. But when we look into the acid pretreatment, the acid pretreatment is generally not preferred because it produces various amount of byproducts it produces, like furfural and other compound which inhibits the biogas production. So people don't generally prefer the acid pretreatment, while the alkali pretreatment is generally preferred because the lignin can be easily degraded by alkali. We can use sodium hydroxide, calcium hydroxide, and other things can be used to degrade it. And the organosolve can be used, ionic liquids can be used, or even something like like when I say the organosolve, you can use methanol, acetone, ethanol, all these things you can use it. But the main thing is that when we use this thing in an industrial purpose or in a large scale, you must, after utilizing it, you must remove all the organic solvent which we have used it. If you don't remove it properly, that might be an inhibiting, it might inhibit the growth of microorganisms. And then we can also use the ionic liquids. Ionic liquids, when we can also use it. And ozone analysis is also one more process which we can use it. Like ozone can be used for breaking the lignin and other things. So this is better when compared to any other treatment because you don't have get much of byproducts out of it. And ozone is basically water soluble, bit water soluble, and also a power oxidant. And the process is good when we use ozones. And you can also, in industrial process, you can also go for the physical and a chemical treatment, like a steam treatment. So you put the biomass into a steam, and then you break down the lignin part, or an ammonia fiber explosion. Like you can use ammonia, you give heat to it, or at a high pressure by putting ammonia you can break it, or even liquid hot water pre-treatment you can do it. So there are various pre-treatment techniques are available. Thereby we can enhance the biogas production. And another important thing is the biological pre-treatment. So in biological pre-treatment, what we do with, we use different types of bacteria and fungi can be used. And these microorganisms, what they do is they secrete various enzymes like lignin peroxidase, lacase, manganese peroxidase, cellulase, xylanase. So what they do is they break break down lignin and other things, that is the lignin peroxidase, lacase, and Mn peroxidase breakdown, while other cellulase, endoglucanase, and beta glucose, what it will do is it will break down the cellulose into the various organic acids and other things. So thereby, the biological pretreatment is better in a way that it doesn't give much of toxic compounds to it. But disadvantage is that it takes longer time, right? So when we see here, the ultimately we can enhance the biogas production. So this I thought to include as an insert, because though I am talking of social issues, so it is a technological innovation which is there. So I thought that we can add a bit of part of pre-treatment techniques can be also included in this seminar, which might be useful for the audience. Right. And then when we look into the biogas, when we come back, we'll come back to the rural technological and things like that. So the challenge is basically the companies which are present in the rural areas are very, very little, and specialist construction, they are all very little. And the biogas is basically done by the rural people. The women only works with the biogas generally. And then if any technical problem comes in, and the women are not that much, no, like they cannot work with it. So to take care of the digester, they generally don't do it. And then the people have lost their trust, and then on the biogas plant, because whatever the government has given earlier, people have worked with it, but after working with it, when people have abandoned a lot, like they say that when a crack comes into the fixed biogas digester, in the when then the crack comes in, the gas leaks, and then who will repair it once again if it has to be constructed, or what would be the cost of it? And the rural people say that no, this I can't do, but rather I'll go to my old cooking system itself, by using fuel wood, or by cow dung cakes. And then and the another thing is the proper management and technical knowledge. Now, why did this fail and things like that? So ultimately a negative perception is created, and people have started abandoning this thing, and the market barrier as well. So so here when we see here, the small and the marginal farmers only, they are the one who should play a major role in the biogas plants, because when they are farmers, they generally have the cow and the cattle and other things, but they they say that they cannot maintain it, because they generally say that our family is very small, I cannot take care of the biogas plants and things like that. And uh, and then the digestate, whatever they use it, since it is in the liquid form, they say that that it's in the liquid form, I cannot carry it to my field. So for me, I would prefer storing the cow dung at one place, and then I would put it into my field. I cannot carry the biogas slurry to my field and do it. It's very expensive and things like that. And the technical barrier is that whenever we need a biogas plant, we need plenty of water. Because when I say mixing means it's 1:10, like 1 kg of cow dung, you have to mix it with the 10 liters of water. So, or it must be at least 1:1 must be there. 1 liter of 1 kg of cow dung is to 1 liter of water. So when people don't have drinking water in those areas, so how can they provide water for the biogas plant? And then in this biogas, there are a lot of impurities which are present, like nitrogen, oxygen, hydrogen sulfide, carbon monoxide, ammonia. All these things are present, and ultimately the heating value is reduced. And people say that we have to cook for a long time in this. So and then they also don't know the proper mixing ratio, how to, because whenever a biogas plant is to be there, it must be mixed thoroughly. There must be proper, at least once, or we must at least mix the biogas digester at least 3 to 4 times a day. Thereby a proper mixing must be done. But in rural villages, in the fixed dome or the floating dome, it is not mixed. You pour it, that is the thing. Whatever the circulation which has been done there, that's it. After that, they don't mix it at all. So because of this mixing things, biogas production will not be there much. And then the environmental constraints. Basically, there might be a leakage in from the digesters. And during summers, what occurs at the temperature, because whenever the pipe is being fitted, it's generally a plastic pipe only would be there. And in summers, when the temperature is very high, the plastic pipe might get loosened, and ultimately the gas leakage carrying into it. So these are some of the environmental constraints. And moreover, if there is a crack in the biogas digester in the bottom, what will occur? There will be a seepage. Thereby, you will find the groundwater being contaminated with these cow dungs. And then institutional barrier, when I say here, the government of India, if at all, if it gives the biogas plant, they must have minimum of 1 to 2 cattle must be there. And then the poorest of the poor, they don't have one or two cows. So they are not eligible for government subsidies. So, and they cannot get a biogas plant. And then like improper networking between them, like for incentives. So whenever any incentive is to be given, so there is like they don't have cows, so they cannot go for it. And then government is also promoting the LPG a lot. So that is a good thing. LPG, indoor air pollution could be clean, but one thing we must look into it, LPG is also a non-renewable energy. It's not a renewable form of energy, because that also will one day. So rather we should go for, government should go for options like compressed biogas, like instead of using LPG, we must go for compressed biogas, where, like when we see here, like in Punjab and in other areas, you have lots of crop burnings are there, crop residue burning. So rather than going for the crop residue burning, we can make some policies, thereby huge biogas plant can be set up. And ultimately, this biogas has to be purified, because when I say biogas, as I said, lot of impurities are present. Now these impurities must be removed, and ultimately we must only compress these methane alone. Thereby, when we compress the methane alone, I think that would be a very excellent thing which government can do it. And I think government is also working in accordance with this thing, for LPG instead of like the compressed biomethane, we can go for it. So when we look into the interdependency of the socio-economic factors, so basically we'll see here the market barriers, feedstock, all are interrelated. So when we see here, we could see the institutional barriers ultimately leading to the institutional barrier, like the socioeconomic factors like market barriers, outreach activities, and livestock. These socioeconomic factor along with the feedstocks. And then the gender participation is also one of the important things here we should see here. Right. And then the low skills and knowledge, low maintenance, and then a negative perception, technical issues. So these are some of the very important socio-economic factors which plays an important role in why people don't go for the biogas plants. Right. Now, what are the various policy recommendations which we have to go for it? So, we should go for a demand driven approach, proper management at the grassroots level. We must go for the bottom up approach. Uh, we should go for, when I say bottom up approach means like it should not go from the government to the rural village. It must go from what the rural villages needs. It must go accordingly. If the rural villages what it is need, we should go from the bottom up approach. And then there must be a market competition must be there plenty. And the we must also improve the public private partnership. So when I say the public private partnership, why we need it is that in and around the rural areas you will find lot of solid waste are being dumped. Now when you collect this solid waste, municipal solid waste rather, these municipal solid waste you can segregate if the proper segregation is done for collecting the organic waste alone. These organic waste alone can be pulped, and then you have to this pulp can be given to the biogas digesters, and we can get enhanced biogas. The biogas can be we can get lots of biogas from it. So there must be a private and the public partnership should be there. And also the small scale entrepreneurs should be encouraged to use biogas, because when we get the biogas, it's not only for cooking. So biogas can be converted to a genset, that is the generator, and it can produce huge amount of energy. Thereby you don't need to use any electricity if you have got a biogas plant. And then organizational involvement must be there, and proper you must have an organizational setup we need it. And then the education is one of the important thing. Like we must be aware of about the global consequences of carbon and carbon dioxide and other things. We must have got an awareness must be there, and the health awareness must be there, and ultimately the women must be given more awareness, and encourage them to use more of biogas rather than non-conventional fuels, rather than the conventional fuels which they use, that is the cow dung cakes or coal or fuel wood. They must go for prefer the non-conventional energy, and capacity building and awareness generation in the community must be there. So I think these are the things which I have discussed it right now. uh yes, so ultimately what we need is the capacity building and awareness must be there. And when we say the overall government should focus, when I like to conclude it, I would say that the government must give more importance to the rural sector rather than the industrial sector, because the energy poverty is very high in rural India when compared to the urban area. So the rural people should use more and more biogas plants. And when they use the biogas plant, they must use whatever the organic waste it has generated, that should be given into the biogas plant. And the organic waste, for that the main thing what we have to do is the solid waste management should be maintained in each and every households. If the solids are being segregated properly, it would be better for the municipalities and everybody uh, to utilize the organic matter and ultimately generate biogas. And then ultimately the biogas can be used for the nation building process, and we don't need to import huge amount of fuel, petroleum and other things from other countries. So India would be self sufficient if we can use biogas as the one of the energy resources. Yeah, thank you very much.
Thank you, sir. Thank
Yeah.
you for your resourceful insights on biogas energy, renewable energy, and what is the economic and health issues with the traditional fuel, and how we can shift from the traditional fuel to the renewable fuel, and
Yeah.
what are the barriers like technical, institutional status of all over India. What is the status of renewable energy or biogas energy? The session is open for discussion, and if any participant wants to discuss anything with sir, want to ask anything, that right question, you can ask to here in chat box. So I will already said that if you have any question, you can ask in chat box. So chat box having no questions, sir. So thank you, sir,
Yeah.
and
Thank you.
thank you, and we'll move forward for the next technical session. Next invited uh, resource person, and sir, we
Yeah.
wish that you would here present here,
Yes, fine, fine. Thank you.
but
Because I've got one more
okay, sir.
program right now, so I'm leaving now. Thank you. Thank you for everyone. Yeah. Thank you.
Okay, sir. Thank
Yeah.
you.
Yeah. Yeah. Thank you.
So we have to leave, sir, as
Yes. Yeah.
sir is having more duty
Commitments are
to
there.
do
Yes. Yeah.
important work.
Yeah.
So
Thank you.
next speaker we are having Dr. Dhirendra Kumar Chaudhary. Sir, you are here. Dr. Dhirendra.
Yes, I am here. Yes.
Okay, okay, sir. So okay, welcome you, sir.
Thank you.
Okay, so before Dr. Dhirendra Kumar Chaudhary will say about his research topic, and what is uh, his expertise. So I would like to introduce Dr. Dhirendra Kumar Chaudhary is a scientist and assistant professor currently serving as the head of the Center of Renewable Energy at Professor Rajendra Singh Institute of Physical Sciences for Study and Research, VBS Purvanchal University. He has extensive experience in the field of photovoltaic devices, having focused on photophysiological and investigations of organic and perovskite material, as well as the fabrication of photovoltaic cell during his PhD and postdoctoral studies. Dr. Dhirendra Chaudhary has held several notable positions in his field, including a 3-month fellowship as a CRE visiting faculty in the research group of Professor Sanjay Mathur at the Institute of Inorganic Chemistry, University of Cologne, Germany. He also worked as a research associate at the Center for Advanced Functional Materials at the Indian Institute of Science, Education and Research, Kolkata, where he focused on the synthesis of peroxide quantum dots and nanoseeds, as well as the fabrication of peroxide solar cell. In addition, he worked as a project scientist at the National Center for Flexible Electronics at the IIT Kanpur, where he was involved in the efficiency improvement of organic solar cell for the translation of efficient organic solar cell for on paper substrates. With over decade of research experience in the fabrication of solar cell, Dr. Chaudhary is an established expert in this field. He is currently guiding 4 research students and overseeing 7 projects sponsored by various organizations. We again welcome you, sir, and please just put light in this workshop, and we are very eager to hear. Please, the stage is yours, sir.
Thank you, Dr. Deep Chakravarti. First of all, I would like to thanks to organizer who have given this opportunity, especially Dr. Bhardwaj, Abhishek Bhardwaj. So I would like to thanks him also to given me and providing me this opportunity so that we can interact with the students. So I'm sharing my screen. Is it shared?
Yes, sir, it is shared.
So I have prepared this presentation for as Dr. Bhardwaj suggested for for basic know how what is going on and few of our works. So I'll go by that only. So in this talk, I'll discuss about advancement in emerging photovoltaic technologies. So I am basically from Jaunpur, Veer Bahadur Singh Purvanchal University, and we are situated in this Professor Rajan Singh Rajubhaiya Institute of Physical Sciences for Study and Research. So I worked under Center for Renewable Energy, so which is recognized as Center of Excellence in Solar Energy by Department of Department of Higher Education, Uttar Pradesh. We deal with different kind of solar cell activities like flexible solar cell, solar driven water splitting, thermoelectric devices, so on and so forth. So we have some good facility as central research facility. I means interested students can send their samples for their characterizations. The content of my presentation is I will briefly introduce about the field, why renewable energy, why photovoltaic is important in context of India, and what are emerging photovoltaic devices. Then I'll discuss on organic photovoltaic devices, different kind of organic photovoltaic devices, with some example, what are the fundamental mechanism for OPB devices, role of nanomaterials, and current status, what people have done and what we have done, few of our work, as well as I'll further discuss on nowadays I'm more focused on development of perovskite solar cell devices. So I'll discuss few of our result which has been published or under communication. As we are in fast growing population, and dependency of human being has caused an energy consumption, and it is increasing day by day. It has been predicted that by 2050 the energy gap would be 15 terawatt around the world. And presently, for energy production, we are prominently dependent on fossil fuels, and this dependency is one of the reason for a globe means increasing consumption of fossil fuels to meet our energy demands, which considered as one of the reason for greenhouse gases. So if you see this graph uh, presented by NOAA, USA agency. So October CO2 is increasingly year by year it is increasing, and the overall impact is going to happen like we are means overall Earth's temperature has been increased from by 1.1 degrees Celsius, and that is causing ocean acidification, as well as rise in sea level and decreasing ice at polar sides. So those are pretty critical things which we should address in our research goals. Therefore, to reduce this dependency of fossil fuel, we should look towards clean, green, and sustainable energy sources which can produce efficient energy without harming our ecosystem. So available energy resources are wind energy, geothermal, solar, hydroelectric, biofuels, thermoelectrics. So these are available energy resources. We are working on these two things, these two main topics, and I will discuss on solar cell specifically. So one can say why photovoltaic is important for I mean photovoltaic is solar cell are more important in other in comparison to other technologies. So if you see this plot, like solar energy means global horizontal irradiation overall spectrum. So if you see, the India is one of the tropical country, and it receives solar radiation almost throughout the year, which amounts 3,000 hours of sunlight. This is equal to more than 5,000 trillion kilowatt among all part of India received from 4 to 5 kilowatt for solar irradiation per meter square. So if we calculate all these, and this is equal to 2003 means 2300 to means 3200 sunshine per year. So these are pretty enormous energy that if we can harness some a fractional amount of this energy, so we can get to know some better efficiency, or we can get self-sustained or sustainable energy resource. So these are emerging PV devices in which dye synthesized solar cell, perovskite solar cell, perovskite silicon tandem solar cell, organic solar cell, organic silicon tandem solar cells, and different kind of quantum dot solar cells falls. I will discuss briefly about organic solar cell as well as perovskite solar cells in which we are working. So why organics? These are the means photovoltaic emerging photovoltaic devices. If you see organic and perovskite solar cell, these can be fabricated on flexible substrate, and these are advantage. Both can be fabricated, and advantageous part of these devices, these can be integrated with buildings. Like if you see this panel, like this is one, this is the real image, like uh, I took it from Google, and that company had fabricated, means install this semi-transparent solar cell at their windows, and they are harnessing the efficiency power, as well as these devices are very lightweight and flexible, so we can use in these devices in many like lightweight energy. We can fulfill our lightweight energy requirement. So if we classify this solar cell generation, so first is silicon crystal wafer based, second is thin layer amorphous silicon based, third is multi-junction solar cells, and fourth is organic, and this fourth is organic or this means emerging photovoltaic devices. So advantageous part of all three, above all three, first, second, third, are they are highly efficient, and they are no like means cost effect, but they are not cost effective, and they cannot be fabricated, or they have some limitation on fabrication on flexible solar cell flexible solar substrate. So in this contrast, organic photovoltaic devices and perovskite solar cell devices are so prominent, like they possesses organic material, possesses high absorption coefficient and very flexible, but their efficiency is low in context to these. Like nowadays efficiency of PV device, OPV devices has reached up to 18%. So now it is not that much low, but in context to um, um, cadmium telluride or other devices, these are pretty, means differences are there. If we classify in on inorganic solar cell, they possesses low absorption coefficient, and organic materials high absorption coefficient, high high processing cost in inorganic materials, large area devices cannot be fabricated, non-flexible, and binding energy is up to few MeV. Whereas in organic solar cell devices, large area fabrication is possible, roll to roll possible, flexible devices is possible, and low processing cost. That makes it no a better solution for cost effective PV devices. If we go through this molecular orbital theory, like these organic solar cell devices fabricated using pi conjugated molecules. So I feel students are might aware about this, how this partial overlapping form this pi bond, and the materials or organic materials which are which possesses these pi bonds are defined as pi conjugated polymers. Okay, so these are conventional organic semiconducting materials. So CuPC, copper thiocyanine, P3ST, poly 3-xylthanamine. So these are few of them are whole transport material, and these are their HOMO-LUMO position, like highest occupied molecular orbital and lowest unoccupied molecular orbital. So YPV is of processing eco-friendly, flexible devices, cost-effective. If we go to basic architectures, OPV devices can be fabricated in these basic architecture like single layer solar cell, bi-layer solar cells, and bulk heterojunctions. Everyone have some limitations, so we'll go one by one. So if we understand single layer photovoltaic devices, these are single layer photovoltaic devices. And in single layer photovoltaic devices, organic material is sandwiched in between top and bottom electrode. Among one electrode should be optically transparent, and when light fall, so electron excited, and they create some these excitons. So due to potential difference, it move towards one electrode, and it get means free, means excited electron, means this exciton get break, and we got some free electron hole pairs. So this mechanism is for single layer photovoltaic devices. So limitation is that, like in organic materials, this exciton diffusion length is pretty small, like 20 nanometer, and with we can, due to this restriction, we cannot to fabricate organic solar cell, means organic layer higher, much higher for efficient absorbance. So this is one of the limitation. Therefore, people come up with this idea, like they use one donor and one acceptor material, in which electron exciton get exciton created in donor part, uh, and then it is mitigate toward electron and a hole, mean this electron conducting and hole conducting layer, electron donor and electron acceptor material, and that get separated. So different terminology is there for, like, if you one can say electron donor or whole transport material or electron transport material. So in one sense, they all are same. So this is working characteristic how these devices work. If we talk about this bulk heterojunction, so what happened? Means we blend this electron, means absorbing and this electron donor and electron acceptor material together, and we form one single layer. So due to this inter blended mixing, we got like very small diffusion length, and in that case electron absorb, and that go to diffuse across the junction, and bound pair dissociated, and therefore after dissociation, these free electron and whole charge carriers got collected. There is not only collection phenomena, there is some no exciton decay and recombination, geminate and non-geminate recombination of bounded electron pairs happens. So we should design our devices in such way like these both recombination phenomena should be avoided. These are basic this IV characteristic under dark, as these devices are diodic in nature, so we get diodic characteristic, and when these light fall, so we get this light negative direction is in opposite to that, so we get negative current, and there is voltage generated across the devices. So VOC is defined as open circuit voltage, and JSC is defined as short circuit current density. So from there we can calculate JSC. We from this P maximum power point we can calculate fill factor of the devices, and using formula P max over P incident we can calculate the efficiency of devices. This is equivalent circuit, and for ideal calculation, for ideal means for best performing devices, series resistance should be as low as possible, and shunt resistance should be as high as possible. These are some other parameters on which we classify the advancement of these devices, like efficiency of these devices, external quantum efficiency and internal quantum efficiency. So all these devices are estimated, calculated efficiency is calculated at AM 1.5. These are some device architecture. These devices can be fabricated in regular architecture and inverted architecture. So these are some typical modification method by people people have used, like where these nanotechnology or have you utilized for device designing uh, good kind of devices. So the challenges are electron and hole transport layer, device efficiency, diffusion length of exciton, trap level, miscibility, internally blends. So I'll take few example from different publications. Like they introduce Jadeno nanoparticles and Jadeno nanostructures, and due to formation of these Jadeno nanostructures, some repelled surface form, and they got some improvement in devices. Thereafter, one another example is like Jadeno have some little limitations with its conductivity. But when we dope some metal in Jadeno, so conductivity can be attuned by conductivity of Jadeno can be attuned by metal doping. So people have utilized this approach, and they got some better efficiency. Like in this paper published in Polymer in 2015, they doped the aluminum doping, and they initial devices with Jadeno only, they were getting 2.79% efficiency, and then they got 3% efficiency with the AZ 8 minutes. So that is irradiation time. There are other some introducing some different kind of electron transport layer. So these are another aspect by which people can attune device efficiency. So here they got some 10% device efficiency, and thereafter electron transport layer by gallium doping. These are some other lithium doping. These are some uh, perspective by which one can attune device efficiency. So it is under process, like people, lot of research work is going on, and different approach are being used by different experts working in the field. So this one is using one copper indium sulfide modifier layer, and they got some different efficiency. These are some efficiency were means improvement. How can I purposely keep these in this presentation, so that student can get aware, like how and how can we attune this device efficiency of organic solar cell devices. And another perspective of this self-cleaning anti-refractive material, designing of self-cleaning anti-refractive material, so that our devices cannot get dust from top, and it can clean itself. So these are another approach which students can look forward for their research endeavors. Apart from this, I would like to come on my presentation, like what we have done in this particular work. So what we did, this is our work. What we did two kind of experiment. Like in one experiment, we incorporated different amount of aluminum, and after doping, what we observed, like by aluminum doping, the work function of devices can be or work function of aluminum azo can be attuned. So using this approach, we dope different kind of different concentration of aluminum in ZNO and define that as AZO. So if you see here ZNO AZO 2%, that means 2% of aluminum, 2% of aluminum concentration is there in context to ZNO. So we fabricated devices. Our initial devices were showing 3.9% device efficiency, but when 3% of aluminum doping we performed, we got 4.3% efficiency. So why this efficiency were increasing? We estimated, and if you go through this GV plot, this GV plot shows like these aluminum goes to some vacant sites of ZNO film and fill. Therefore, ZNO film traps from ZNO film get reduced, and we got some better efficiency. Therefore, thereafter, what we did, we passivated in other set of experiment, we passivated ZNO with PCBM. PCBM is a polymeric material, so it would not be doped, but it was in blended form of in ZNO. So it is hybrid kind of it is nano composite of ZNO and PCBM. And what we did, we added a fractional amount of PCBM in ZNO. Thereafter, we estimated the work function of ZNO and ZNO PCBM. So then what we got? If you see here, ZNO only work function of ZNO only in thin film was 4.56, whereas in case of ZNO PCBM, it got reduced. So due to reduction of this, we can get some smooth charge transfer, and that smooth charge transfer facilitate better efficiency. Here with PCBM, P3ST PCBM system, we got 4.49% efficiency. So this is one of the means best reported efficiency with the P3ST PCBM, and one patent we have filed for this, and that is under procedure. Thereafter, what we did, we use some no benign solvent like xylene, apart from this dichlorobenzene, to make sustainable devices. Like if we are using dichlorobenzene, that is not good for the health. So what we tried, we utilized xylene, and we were getting some good efficiency from those devices. These work are under no communication, so I'm not going in that much detail. Thereafter, what we did in this section, like we synthesized some silver nanoparticles and we deposited on top of ZNO. If you see, go through this micrograph of AFM micrograph, then these small dots are ZNO nanoparticles, and we fabricated some PCDTB BT PCBM solar cells in inverted architecture, and we got some efficiency 5.74%. So these efficiencies, furthermore, we in recent work after joining here, we are working on these semi-transparent OPV devices. So these, if you see, these small devices are pretty transparent, and this work is recently published, and we fabricated semi-transparent solar cell devices with efficiency 2.44%. So that is in the context of semiconducting, semi-transparent devices, that is pretty good efficiency. Now in next part, I would further discuss on perovskite material and perovskite solar cell devices on which we are working. So perovskite materials are material which are in form of ABX3, and their crystallographic structure is shown here. So the challenges, I'm directly coming to challenges. So challenges with perovskite perovskite solar cell devices, or like these devices means growth of perovskite film itself is a very challenging thing. Like compact perovskite layers cannot be grown, large area and ion migrations, and presence of lead in the devices. So in this talk, I will discuss three of these things. Like we have carried out some work on what we synthesize a set of quantum dot material, and what we did, we modified with the quantum dot. And so in this process, perovskite grains are like pretty tedious to optimize. Means getting same kind of morphology in perovskite solar cell is pretty tedious. So means there should be we should have this compact layer, and this compact layer should be hole free. As so, what we were getting in our preliminary research, when we were treating our films with chlorobenzene, that is anti-solvent with DMF, so we were getting larger grain size. But due to formation of this larger grain size, there some pinholes were forming. So at the same time, we have synthesized some quantum dots which were on in size of uh, 8 to 10 nanometers. So what we did, we synthesized these quantum dots, we dispersed in chlorobenzene and treated. So thereafter, these are some photograph of these as synthesized quantum dot, TEM and XRD. We characterize these quantum dot very systematically. So if you go through these SEM micrograph, in first panel is just grown samples, like just deposited perovskite. In panel B, anti-solvent only treated. In if you compare A and B, there means grain size, there is definitely after chlorobenzene treatment, grain size were higher, we were getting larger grains, but there are some pinholes. So what we did after this putting these quantum dots in chlorobenzenes, we got no very compact quantum dot. Oh, it is not moving. Quantum dots were passivated in these pinholes, and we got very compact layer. So these compact layer were not only filling with the filling at the surface, these are forming bonds and connecting these adjacent grains with this. So if you see this high resolution TEM, it's if you see this HRTM, so these are quantum dots, and these are bulk quantum bulk perovskite. So we form a bridge between the two means two systems, like two bulk perovskite grains using quantum dots. Using this technique, and we characterize this very systematically using different techniques. We recorded, means this this grazing incidence XRD, so that we can get how these quantum dots are distributed. So we found on surface mostly quantum dots are distributed and as well as filled in the voids. So with this efficiency, means with this optimization, what we got, initially we were getting some 12.9% efficiency, and after modification we got 16.5 or approximately 16.5% efficiency. This modification not only improving device efficiency, but we got pretty stable devices, because this in quantum dot we optimized with BR 1.5, I 1.5, and BR 1. Due to presence of bromine, this 1. BR 1.5 quantum dots are pretty stable, so that were restricting the mitigation of oxygen and this H2O molecule in perovskite, and preventing from deterioration. We fabricated using, since we were able to form some large compact films, so we fabricated some large area devices, and we got 12% efficiency. So these are different characterizations. I'm not going to that much details. So thereafter, we utilize another set of modification method, in which we used CZTS and coarse cell CZTS AU structure, and blended with perovskite system. So we synthesize different kind of different size of CZTS quantum dots, and which size distribution was some sort of 7 nanometer to 11 nanometer, and we characterize them systematically. Thereafter, we synthesize some gold CZTS nano structures, and we characterize them by different methods. So we were getting gold and CZTS core cell structure, and that were means characterized by different head of. If you see go through this head of image, this white spot is gold, as well as this dusky side is CZTS. So what we did, we removed the olelamine ligand from we replaced olelamine with methylamine, and after removal, if you see here in CZTS quantum dot without any treatment, there are olelamine is there, but after replacement with methyl ammonium iodide, this olelamine ligand got removed. If you see here in TEM mapping, so copper, zinc, tin sulfide is pretty well distributed, and this and these are cross-sectional SEM. And after, if you see, go through this UV visual absorption spectrum. So in case of S deposited films, the absorption is up to 800 nanometer. But when we put some CZTS in the perovskite material, so absorbance increases. This absorbance increases due to presence of first of all, we form some compact layer. So there is enhancement in absorbance, as well as we are getting some extended absorption region. So that comes from CZTS, which is present in perovskite material. We fabricated and optimized the devices, and we got efficiency 16.5% with this system, in which was in CZTS for 90 minute growth of CZTS. So this was happening because we estimated the pore size of these mesoporous TiO2, and pore size formed in mesoporous TiO2 was some approximately ranging in 10 nanometer. So in case of 90 minute, we are getting 7 nanometer size of CZTS quantum dot. So due to that, we are getting with these devices were showing good efficiency, whereas 120 minute was not, because these were blocking the pore site, and we are not, means perovskite is not passivating within TiO2 mesoporous film. So with this, we got some 19.97, approximately 20% efficiency, and we optimize by different method. In recent work, we means this we did guanidinium modification. So we used a triple cation perovskite system in which cesium, formamidinium, methylammonium, lead bromide has been utilized, and guanidinium incorporated. So in case of pristine perovskite, if you say, we were getting some random oriented perovskite of smaller size, whereas in case of guanidinium incorporation, we are getting some larger grain size and very compact and uniform layer. So what we got, like after this, we got no guanidinium placement of guanidinium. We got high this this high contact angle. So due to when we are placing this guanidinium iodide in perovskite, so first of all, it is forming some bonding with the perovskite, and guanidinium is hydrophobic in nature. So therefore, we got improvement in contact angle. Thereafter, we characterize these perovskite films by different technique, and we got device efficiency up to 16%. So interesting part of these devices, like these devices are pretty stable, and we are still measuring its stability. Thereafter, we encapsulated our devices with the quantum dots, and we have I would like to share one video. So before going, okay, how can this entire screen share? Mhm. Share this video first. टॉक में है सर कुछ दिन बाद. Okay, so where is this? Oh, yes, I just want to share this video. Yes, this panel is visible.
Yes, it is visible.
Okay, so it's
Start the
alright.
video, sir.
So yes, so for means hydrophobic work, we recently worked with the University of Cologne. So what we did, we synthesize one hydrophobic material and coated on top of perovskite devices. So if you see the advantageous part, if you go through this, like this is the non-coated devices as fabricated, and when we put inside the water, so it just drown. Thereafter, we spray coated hydrophobic film on top of our devices, and thereafter we recorded the contact angle. So if you see here, these the water droplet were not even sticking, and when we completely removed, so it just ran away from the devices, right? So what we did, we put some more order, and it just run out from the device. And thereafter, what we did, we place our device on top of, we just place our device in water, and our devices are floating. So I'm not going in much detail because this work is under patent thing. So that's all I think. We have worked some semi-transparent solar cell devices also. We are still working on it. With this, I would like to thanks. I think I am completed. I completed on time.
Hi, yes, sir. Obviously, and thank you, sir, for your
And one more,
yes.
this announcement for students who are available here. Like I am coordinating faculty at Center for Advanced Material Characterization Center, which is a central facility of our university, central research facility. So we have FESEM EDX and HRXRD, which is equipped with grazing incidence, small angle, wide angle, apart from that thermal conductivity constant analyzer. So students, they can, if they are interested, they can send their sample for their characterization with view channel. So thanks.
Thank you, sir, for this information also. Because
Yes,
nowadays the research is based on the scientific instruments, and which is very more needed for our better publications.
yes.
So so this forum is open for discussion. If any participant want to ask any questions, the relevant questions, then they can ask. And as I can see that the chat box is not there and not having any relevant question. So I'll before going to the next resource person, I just will say something that about the sir presentation that we have discussed. The sir has discussed the photovoltaic cell and their generation, inorganic and organic photovoltaic cell devices, and different nanocomposites, and his inventions like perovskite materials and recent photovoltaic devices he has developed, synthesis and characterizations of those photovoltaic devices. And thank you, sir, for this resourceful informations and during this 1 hour. And we are fortunate enough to have you on this forum.
Thank
And sir, we wish to have you in this forum until 5 if you have any, don't have any work.
you. I will be. I will be.
Okay. So that it is time for the next resource person, Dr. Abhishek Kumar Mishra. Sir, you are here, sir? Okay. Okay. Welcome you, sir. And before going to your talk, before you just explore your and present your work, I would like to say something about you. Dr. Abhishek Kumar Mishra is presently working as associate professor at Department of Physics, UPS Dehradun. His area of research has been materials and modeling and simulations, density functional theory, molecular dynamics, force field calculations, machine learning. Dr. Mishra has been working on CO2 capture and conversions, gas sensors, 2D materials, thermoelectric materials. He has received 7 research grants on various research projects and 5 awards for excellence in his research domain. Dr. Mishra is also an affiliated member of Royal Society of Chemistry, London, UK. He has published more than 62 research articles in various reputed international and national journals. I welcome you, sir, and the stage is yours. Please, sir.
Thank you, Dr. Deep, and I'd like to thank you, Dr. Kuldeep, as well as Dr. Nidhi, for inviting me to this very nice workshop. Guys, the screen is visible or not?
Yes, sir, it is visible.
Okay, thanks. So, as Dr. Deep introduced, my work is on computational modeling and simulation of materials, where we are using the principle-based simulations as well as machine learning to design and explore new materials for various applications. And one of the main area in which our group is working is designing the catalyst for CO2 conversion. So, as the theme of this workshop is towards the renewable energy, so I have chosen the specific research interest towards the CCUS, and in the next 50 minutes or so, we will be discussing CCUS and how you can explore these materials at the nano level for efficient conversion of CO2 into something of the industries. So if you look at the energy consumption in different sectors, it's mainly consumption is towards the industries. And in the different industries, chemical industry is one of the most energy intensive industry. The second largest industrial energy consumer, and they use fossil fuels both as a raw materials and as a power and fuel, accounting about 14% of the total industrial energy consumption. So if you can replace the part of the fossil fuel consumption by renewable energy, in particular, specifically uh, focusing on the chemical industries, it is a central strategy for resource and energy efficiency. So the overall, what I'm trying to say that if you can use the renewable energy sources in the industries, particularly in the chemical industry, this is a good win. So for turning the gear towards the CCU and CCS, uh, if you look at the pre-industrial environment and now how it has been changed, that is the result of using more and more fossil fuels in different industries. Uh, I mean, the CO2 concentration from 280 ppm in 1950 has been going day by day and 426 ppm at this 2024. So if you look at that few years back, about 15 years, 10 years, 15 years back, people were mainly focusing research on the CCS, how they can capture. Capturing was the main research area where this particular domain was interested in, and then how can store that. Of course, there are many techniques: pre-combustion, post-combustion, oxy-fuel combustion, capture, and there are subdivision as well, like at Jobson and Jobson. People have been using metal organic frameworks and various materials as well, but they suffer from their own uh, issues like potential leakage, huge energy consumption, and disruption of the system. As a result, now people are combining these techniques with and their more CCU. So uh, the aim is not only how you can capture or you can store the CO2, it's more towards how you can utilize it. And if we specifically talk about the CCU things, it's basically first capturing and of efficient catalytic systems to convert to gas into different chemicals or even fuels. And as you can see here, people have been using different materials, specifically ionic liquids, metal organic frameworks, uh, even metal clusters, combining with the transition metal oxide based catalyst for these CCU things. And even the now at the moment, the research is focused on the integrated approach. The integrated approach means focusing on dual functional materials. So dual functional materials means the materials which act as a capturing agent as well and converging as well. But once you are capturing and then extracting, it is a huge extensive energy extensive task. So the focus is towards developing those methods which combine the advantages of capturing as well as the conversion. So if you look at the CCUS as a broad, it's everything. It's a capturing, it's separation of CO2 from the exhaust gas, refine and capture CO2. It's somewhere storage as well, and utilization as well. So use CO2 as materials for different products. It can be formic acid, methanol, any other fuel as well. So what basically the CCUS is this involves the capture of CO2, and let me use my PowerPoint. So this unit involves the capture of CO2 generally from the large scale sources, and basically from industry that we have been seen, and then store it and transport it by different ways. But those things involve their own risk of leakage as well, and then the utilization part. And if you have to utilize it, the first name comes into picture in the catalyst. So catalyst, or I'll say the catalytic reactions, should be designed to run at lower temperature and pressures. But if you need high temperature, which is the major issue in the catalyst cases, that means that you are giving some energy out of your pocket to convert CO2 into fuels. Then again, like it's not the good thing because you are wasting some energy. So the catalyst should be effective enough at the lower temperatures and pressures. And this research so far have been focused on the trial and error actually, because basically you go synthesize and check at the catalytic activities. And here comes the role of computational solutions. Because they are they're really important. So they can guide the experiments towards catalyst design and development by working on the atomic level information. So if you have to design the catalyst, they have their own challenges like activity and safety of catalysts are low. And uh, we have to deal with the improvement in the rational design of catalyst. And here comes the role of computational solution. And one of the strongest powerful method that people have been using in this area is the DFT, which I will be describing more into detail in the next slides. It's a first principle based approaches actually. First principle based approach means they are ab initio approach, and you need not to have an experimental data to start experiments. And that is the main one of the powerful advantages of these techniques. You have you can use these techniques to design the catalyst and if I can remove these lines that I have made. So if you look at this computational scenario, there are many methods, of course, which are useful to design catalyst and materials at this level. And one of the most strongest method is the one which I just described, the DFT simulation, which are also known as electronic structure calculations. And the first, and that's also one of the first stage where you design a build a atomic scale structural model, and you calculate the energies for the elementary steps in the reaction mechanism. And then once you're done, these are really strong calculations. Once this is done, you can do the Monte Carlo simulations where you can fit those energies in the microkinetic models. Of course, as a third step, because you have the real materials, though you may include the incorporate the coarse graining models, and finally the effect of temperatures as well. But in the whole scenario, actually, in this computational modeling aspect, where you start from the DFT, you do macrokinetic modeling, coarse grain modeling, and then you include the effect of heat as well. But all these, as you can see, if you start from left to right, you have to just a second. Yeah. So the time for these calculations increases with the as you move towards these different scalings. So coming more specific into the catalyst design, as you can see, it's a three-step process. The first is the capturing, as I said, that you can do capture by using ionic liquids, you can do by metal organic frameworks, using amine-based systems, or even you can have a catalyst over which you put some metal clusters and you can store them. And uh, it depends upon the capturing agent. They have their pros and cons. However, the main thing which I'm trying to highlight here is the second and third is the three-step process. As I said, so extraction and conversion is really, really important. And this is an energy extensive task where you need to reduce by any means the cost and energy so that your catalyst is effective to use. So I'm going to present some case studies in this direction to motivate you and to present the effectiveness of these simulation techniques, first based techniques. So we started a few years back working on the copper oxide catalyst, and the reason why we choose the copper oxide because if you look at the literature, is still one of the unique metal which can produce large hydrocarbons, the copper electrodes. But they have their own disadvantages. As I mentioned here, they have limited energetic efficiency. They lose their CO2 reduction activity in the environment, and that is the reason people have been uh, focusing on the oxidized form. So the experimental data is available on the direct reduction of CO2 ethanol at the oxidized copper electrodes. And even if you compare the steam copper electrode with the oxidized ones, you will see the increased methanol formation. So these are the advantages of using the oxidized. Copper. And even and I mentioned here that uh, there is a mixture of copper and copper two oxides and copper oxides. So when you are going to synthesize these materials, you at the surface, whether it is a copper one or copper two, you're not sure actually. So because it really combines with the oxygen and changes their oxidation states. So uh, we have to start with a model which can effectively model the both copper one and copper two oxides. Now, this is the bulk material structure shown in the left side of the screen. And experimentally, if you try to dig out the information about copper oxide bulk, it's a monoclinic crystal insulator having band gap of varying band gap between 1 and 1.2 or so. It's a magnetic material. But if you do the simulations from the DFT, which is everybody is saying that is one of the strongest techniques, you will see that the pure form of DFT predicts the electronic toss like this. If you look at the here, the dotted line here is showing the Fermi energy. Fermi energy, and you can see here that there are some states which are crossing at the Fermi, which means that we are getting the continue to read zero band gap, which is not the case. As I said, that experimentally it is well known that it has a band gap. So the problem here is, I mean, the why I have put these things details here is to give a technical glimpse of the using the appropriate methodology before you start doing such calculations. Now we have seen in even in the catalysis applications, these things affect a lot when we calculate the activation energies. So there are many functionals in the DFT, and in the GGA approach, the plain DFT approach, the main problem is electron self interaction, which has been ignored in the formulation of the pure DFT. And there are other methods high level, but if you're going to use those methods, of course, you have to uh, huge number of computational resources, and it may take even for the catalysis applications, it may take a infinite number of types of calculations. So that is the reason people have been using the semi-empirical method where they fit a particular parameter, which we call it as a Hubbard U parameter, and try to repeat the model which can predict the reasonably good properties. Going a bit more technical, here you can see here that we varied the U parameter on the left side, and when we were at the range of we varied the U parameter, and as you can see here that at around 7 U parameter, the band gap as well as the magnetic moment were in the range. And that is the reason, I mean, we chosen this U parameter. And as I said that you're not exactly sure whether you have copper 1 or copper 2 oxide at the surface when you're doing, whether you're going to study the catalytic reactions. Hence, our aim was first to be sure that whether our model is good for both, and we found reasonably good agreement with the magnetic moment as well as the band gap for both the parameters. And now the second task in the modeling is, I mean, you're not going to work on the bulk material, you're going to work on the materials. And when nanomaterial comes into the picture, you see that you can have different kind of surfaces. So our next task is to identify what kind of morphology you can have in the experiments. And before I can start doing such kind of calculations to calculate the surface energies of different low index surfaces, you need to understand that you can have different kind of surfaces. The type 1, as I mentioned at the top, is one of the surface where you have anions and cations as equal numbers. So that's a type 1. And the second one, you have the particular charged plane. You have repeat units like -1 plus 2, -1 plus 2. So the net dipole moment, there's some net dipole moment. So these are the polar surfaces actually. And the third one, the right side is the third type of surfaces, which you will see that, okay, you have minus, plus, minus, plus, you have charged planes, and but as a result, you have dipole moment normal to the surface. So these surfaces also unstable surfaces, and you will not be having such kind of surfaces experiments. So that is the reason you need to reconstruct such kind of surfaces before you can start your model. And just presenting our results here, as you can see here that our copper 1 seem to go. I found this kind of different low index surfaces. We calculated the surface energies. And if you look at the surface energies, even 111 surface have two different termination, oxygen terminated, which is shown here. Copper terminated can have as well. and then 114 surface and 1 surfaces can have their terminated and proper terminated series. If you look at the surface energy values, you will find out that 111 surface with oxygen termination have the lowest surface energies. And this is represented in the morphology, which I have presented in the center of the slide. You will see that 111 plane is the most dominant planes in this morphology. But there are other surfaces which are available, but have less exposure. And we also calculated the work function and which was to be in the experimental range. And this is the scenario for the other copper oxide, CuO, which is a magnetic material. And you see that on the left top side, you have a bulk, and you can have the different kind of magnetic ordering as well. You have a bulk like, or you can have a line by line, this line, this line, this line, or you can have a layer by layer. We did calculations to find out what kind of ordering will be existing in these surfaces. We have examined these different low-kinetic surfaces. And you will see here uh, you will see here that there's a particular case and having two layers of copper oxide CuO surfaces. That uh, one surface, you will see that the binding energy is minus 71. While for the 010 surface or the other ones, you have and double of what we have here in the 111 surface. So this is quite good actually. I mean, this makes sense because if the surface is more stable, it will show the less reactivity towards the molecule or any kind of surface reactions. And if the surface is a bit unstable, it will be available for any kind of surface reaction. And that's what we saw here. And we did further processing calculations to identify how much CO2 is activated. So you will see here that there's some charge transferring is occurring between the surface as well as the molecule. And we also did the phonon calculations and saw that if, sorry, yeah, and saw that these are the vibrational modes for the isolated CO2 molecule, and these are the one on the one surface. And you will see that they are changing. So all this calculation, the beta charge analysis, the beta charges versus charge density difference calculations, non calculations, geometric calculation, banding energy calculation, all represents that these surfaces are capable of activating the CO2. To is activated, and that was the first part in the catalysis design that first the molecule should interact with the surface. And our calculation, our part is not done. So if you remember that we are focusing on the CCU, the carbon dioxide utilization. We're not focusing our work on the capturing. Once it interacts with the surface, we have to look at how we can convert CO2 into something usable in the industries, chemical industry or somewhere. So what we did, we look at the co-absorption of CO2. This is green oxygens are depicting the oxygen of CO2. This is a gray one, a small dot is showing the hydrogen. So we found that two sites where which hydrogen, atomic hydrogen can interact. One is, I mean, both are equivalent. These images are one image of a one surface of oxide. So the next task is to identify how this atomic hydrogen is going to connect with the CO2 to form something. So this is the one set of calculations. If you look at this calculation, you will see that um, you need a high barrier, about 3.35 electron volt, to in order to have this oxygen, this hydrogen connected with one of the oxygen CO2 molecule. So this is one of the well-known path of formic acid, which is known as carboxyl pathways. If you have to go to the carboxyl pathways, you have to give a lot of energy to your system, and indirect and or in other ways, I can say that okay, this is not the path that you may follow in conversion of CO2 on copper oxides. However, look at this. Just 0.14 electron volt energy is required if you have to connect hydrogen with the carbon atom of CO2. And in the second hydrogenation step, if this is more energy favorable reaction, and in the no time you will form the formic acid. From this series kinetics calculations from the first principle simulation, what we found that copper oxides are a good catalyst at room temperature for converting CO2 into formic acid, and the path that you are going to have. Okay, then this was a paper published, and then our experimentalists in the collaboration did such some kind of experiments. These are the results of the drift analysis, where let me briefly introduce what I'm depicting in this figure. What they did, they started from the copper oxide nanoparticles, CU2, and in the chamber, and they bombarded the hydrogen gas over it. And in the no time, they found that the CuO was reducing into Cu2O and finally copper. And if we discuss about the product, you can see this is the only one peak from these things. And the format was one of the product they found point where Cu2O is. Okay. So there were two puzzles. Why this CuO was changing, reducing into CO2 and finally copper. And the second question was in the experiments that they were not able to understand also why only format and not the blue one and the green ones, which are the methane and carbon monoxide. So this was the issue. That you cannot actually, you can make some speculation, but you cannot actually determine what is actually happening. And if you cannot determine what is happening at the nano level, you cannot actually design the things. And that is the beauty of the full principle distributions. So we did experimentations and we published as well. We started from the one surface of CuO and placed one hydrogen molecule over it. As soon as we placed hydrogen molecule over it, as you can see here, takes one oxygen out of it and forms the water. Finally, I can say that it is the hydrogen gas molecule. As soon as it comes in the contact with the copper oxide nanoparticle, it forms a surface bound water molecule. Also, second point, as oxygen is getting attached with the hydrogen to form water, the surface is getting reduced. And if you have more and more hydrogen gas come to the chamber, your carbon, your Cu is full now. At some point, it will change to CO2 when it will get reduced. So hydrogen forms surface bound water molecule after interacting with the intermediate reducing the surface of CO2. And after some time, finally, it will reduce, take out these oxygens as well, and you will end up with the copper here. And if you remember the slides that I have been discussing in earlier slides, we discussed it that if you have surface, you will first change into the acid and you will first into formic. If you remember these slides, yeah, you have the formate and then you will formic acid. So what was happening? That hydrogen molecule was interacting with this pristine particle and was reducing them to the CO and finally to and in between this we had the CO2 so side we were getting the formate as carbon. So the other was. We have been working on the vaccines as well. These are fascinating materials in various domains. I've been working on hydrogen gas sensing as well. And a few years back, we investigated vaccines CO2 capture as well. And in a slide, if I'd like to summarize that work, what we did, we engineered the effects there. And once we introduced the defects, what we found that CO2 absorption increases heavily, and you can actually activate the CO2 over these vaccines. And this is the one of the work that we did for years back, revision with the agencies in Bangalore. This is the work on again 2D materials, and our aim was to. I mean, if you look at this triangle, you have graphene here, which is zero band gap semiconductor. You have a boron metal with the insulator, and both have almost the same kind of lattice structures. You have the tyrene and the way, and you have carbon here. So, what motivated Professor Sinarao is to mix these boron nitride into carbon lattice and out of you can have the fascinating structures. And at Shrutism, we had a different kind of challenges here and questions in mind. How does the boron nitride decorate the carbon lattice? How do properties depend on the ordering? When there are two things. One is the composition, concentration of boron nitride in the carbon, in the graphene, whatever you say. And you change the ordering, whether it's going to affect anything or not. So we started from a simple structures of, as you can say, you can see here different kind of configurations. We tried keeping the number of atoms same. So this was the unit cell. It is vertically sliced, and we change the compositions as well. When you change the composition, you will have the DB bonds, boron bonds as well, and nitrogen bonds as well. As you can see here, you have nitrogen bonds here, and you have similar kind of bond. And here, if you look at the this structure, at the interface, you have a mixing here, and at the interface, you have PC and NC bonding. So what we found that such kind of structures are best in energy, and second lowest energy was found to be this when you have an interface, well-defined interface between the graphene and boron, right? That was the as I said that if you have the BB bond, kind of are not likely to in your structures. And the second thing which was fascinating was mixing such kind of lattices result in different structures. And yeah, what we did here, we just double the completely this was on this table. So as a result, we concluded here actually that you have the domains of the nitride in the graphene, and the bigger the size of the nitride domains in the graphene, is the more stable. And we shed light on the electronic band structures and the band gaps. You have a tunable band gap materials here, and also which I think I am not having here. Yeah, okay. You can see here that the band gaps are zero band gap, and so the varying band gap structure that you can have by such kind of. We also did further calculations that we're not going to discuss here, but we did non-CR band, electronic band structure calculations, and some rippling was available at the band structures. Next, towards the environmental applications, I'd like to highlight one of the application of these materials as greenhouse gas absorptions. So, absorption is one of the most promising technology to capture CO2 and methane from the flue gas. And why we were, I mean, why we started doing such kind of experimental competition, because these even materials have the uh, larger surface area compared to graphene. But even BCN are better in terms of the surface area. So yeah, if that was the and this is the experimental observations that even borocarbon nitrides, which we call it as BCN, have high surface area ranging from 1500 to 2000 square per gram high CO2 uptake. So experimentally, what they found that they have, I mean, this BCN have the high CO2 uptake. So our aim was to identify how much CO2 you can have, you can store on these BCN materials. So we started from our basic models of number of BCN atoms equal number of BC and N. We did some preliminary calculations to relax the structures, calculated different the energies, as you can see, optimize energies parameters. These are the DOS. And this was one of the structure that we found as the most stable structure, and these are the just repeating units in the x and y direction. So this is the one unit cell is, which we started actually to do the calculation regarding the greenhouse gas absorption. The details we found BN3 and MB3. We started from the one CO2 molecule, which accounts for the 17 weight percentage, and we tried different orientation and different configurations, as you can see here. And the left one is the BCN, the right one is the graphene for the comparison, and these were the results. And we found about 18.91 kilojoule per mole on the BCN, while here the binding energy was comparatively low, about 13 kilojoule per mole. And you can see that I mean, both are feed absorption low, absorption was found, but still BCN did better. So it binds more strongly to BCN as compared to graphene. And then we did calculation to find out, okay, I know that, okay, BCN is good for CO2 storage, but how much? How much weight percentage? So we did calculation on 2, 3, 4 molecules per cell. And at some point, what we found that when you increase the more concentration, there was no interaction, as you can see here. And we found some repulsion. So we concluded that 44% is the optimum weight percent of CO2 BCN, and at high temperatures, the repulsion between molecules becomes dominant, and at that is not. Similarly, we did calculations for the methane gas. And here again, what we found that this VCM did better compared to the graphene. And we did calculations for methane molecules. And finally, we concluded that, okay, how much is the optimum weight percentage for CO2 and optimum weight percent for the methane or what we see in materials. And these were the sites over which the molecules stored. And this was highlighted as one of the hottest article in the inorganic chemistry in the Chem journal that time. Recently, we have been working toward designing of materials, and we worked on the heterostructure of gallium nitride and boron nitride and graphene. And what we found that these structures are, I mean, as per the calculated formation energy is depicted here, you will see here that these are formation indicators so that we can compute that these are stable structures. Similarly, mixing the gallium nitride with the boron nitride. And what we found that these are the direct band gap materials defined potential application of the optoelectronics. This we have discussed. Yeah. So we have been working on the energy domains. We worked on the infrastructures of graphene and TMDCs, the TMDCs that we worked on here in the half sulfide. We worked on the heterostructure, one graphene layer and one half sulfide, and then we tuned the interlayer distance and calculated the pathways for the lithium and sodium and potassium ion for these infrastructures. And what we found here that they have a high rate capacity, moderate volume expansion, and energetically stable structures. Recently, our lab have been working on the designing new PD materials, and one of them is graphene, and it exists as a half hydrogenated form, which is known as graphene, and a fully hydrogenated form, which is known as graphene. These are these are the 5, 6, 7 numbered rings, as you can see here, and have zero band gap material. I've been working on the CO2 activation of these materials. And what we found that if we look at the pristine materials here, you have a very low binding energy, -15 for the graphene, -18 and -16 over the graphene. But what we did in order to further enhance the binding energy, we took the copper, and we'll see that the binding energy increases about 3 times, about 45 kilojoules. They investigated the stability, the band, and the charge density physical to further quantify the size and the nature of it. We are also working on the defect engineering, and where we are exploring the defects on the CO2 accuracy. What we found that once you have defect on such kind of structures, CO2 is activated more strongly with a high binding energy. Here and in fact with a high. So this is the part of our actually recently grant that we received from the CERB. And this is on the 2D transition metal oxide CO2 capture and conversion, and also investigating them as a dual functional materials. So this is a transition metal oxide, copper oxide, and which what we have discussed. What we are doing here is to explore the 2D form, because they have large surface area, which is very good for the catalytic applications. So we are working so far on um, recently uh, 2D form. So if you look at it, remember that earlier it was minus 56 kilojoule, but here the binding energy is higher than here, and there are existing two forms actually. One is a zigzag structure, one is a flat. So we are investigating it here. Thrombine is another material that people have been able to synthesize, and in a similar way, we are investigating that different mediated CO2 on the thrombine materials. I'm just summarizing what my group is doing here. We have been using the quantum chemistry based tools, so the first principle QMMM, as well as the machine learning tools for materials investigations. The applications, if I talk about, is CO2 capture and conversion, but the other domain that we have been working on here is the materials for gas sensor, thermoelectric materials, and photovoltaic applications, as well as the drug design. So we have received some recent grants from the government as well as industries, and we have recently started working on the ML-based metals investigation for the perovskite-based materials, where we are training the data set and investigating the properties from the machine learning by using different algorithm, and predict those materials and validate them using the computational principle-based methods. This is I would like to thank my PhD students for the contribution of the slide, and would like to thank the UPS seed grants, as well as for the PhD fellowships to the students, computational resources from the University of Denmark, as well as the University of Kassel, Materials Square for the computational grant, and the service for the grant. Thank you. I'll be very happy to take any questions if you have.
Okay, thank you. Thank you, sir. So this forum is open for any question or any query related to this research or related to this workshop or anything. You can ask in the chat box. Okay. Okay. So we do not have any questions, sir. And
we can share, sir, in future if anybody can send us the questions.
yes. Oh. So this lecture is all comprised of carbon capture and utilization and storage, and industrial energy, and also catalyst development and challenges, and about the mixing emerging 2D models like copper oxide nanoparticles, and all the recent development which is Dr. Mishra has developed in his lab and with his collaborative research team. So with this, I am here inviting our chairman, sir, with the technical session, Dr. Vikas Srivastav, sir, to conclude the technical session.
OU SHKA मैं चेक करती हूँ आप चेक कर लो चंडीगढ़
Yes, sir.
So it was a wonderful and informative talk by three of our guest speakers. That is Professor S. Balachandran, Dr. Dhirendra Chaudhary, and Mr. Abhishek Kumar Mishra. Today, all the three speakers have given a very insightful lecture on different topics related to the biogas also. As we know that very well, biogas is very important aspect and a very good source of renewable energy. And as the Professor Balachandran basically discussed about the challenges faced at the rural areas and the myth basically which is spreaded in the community, and he also discussed about the various kind of that uses and applications. So I hope that the lectures given by the all the three experts has given the insight to our audience, and definitely the some of the scholars or participant will carry forward the ideas given by the all the three speakers. I would like to again congratulate to the all speakers for sparing their time for this international workshop. Thank you very much.
Thank you, sir. I would like to thank again Professor Dr. Vikas Srivastav, Co-Chairman Dr. Nidhi Shukla, Professor S. Balachandran, sir, Dr. Dhirendra Chaudhary, sir, and Dr. Abhishek Kumar Mishra, sir, for your thoughtful and innovative ideas, which which have added an extra information in this international workshop. And last of all, thanks to all participants for giving the time to join this forum. Thank you again. And with your permission, sir, then